Tonight, the festival is proud to host two of WVU's own rising stars. WVU physics professors Duncan Lorimer and Maura McLaughlin are known for their significant research on pulsars and are part of an international research team that, through the use of pulsars, intends to detect gravitational waves, which are a key prediction of Einstein's theory of general relativity. Pulsars, discovered more than 40 years ago, are rapidly rotating stellar remnants formed in the explosive deaths of massive stars. WVU has been awarded $6.5 million from the National Science Foundation as part of the international research team called the Partners for International Research and Education Program. McLaughlin is the principal investigator on the grant. So far, the research has yielded the discovery of new pulsars, more sensitive telescopes, and improved detection algorithms. Both Lorimer and McLaughlin teach physics and astronomy courses to WVU undergraduate and graduate students. Lorimer was a recipient of the 2010 WVU Foundation Award for Outstanding Teacher and Cultural Scholar Award. McLaughlin received the Alfred P. Sloan Fellowship, Cultural Scholar Award, and was named a 2009-2010 Outstanding Researcher. At this time, please join me in welcoming Maura McLaughlin and Duncan Lorimer to the stage.
Thank you very much for that nice introduction. And thank you to the organizers for inviting us to be here and talk about our research. It's a great honor to have so many people here who are interested in learning more about pulsars. They're fascinating objects. We love studying them. And we hope by the end of this lecture you'll find them as fascinating as we do. I'm waiting for our slides. Good, thank you. Okay. There we go. Okay, we need to have the movie. So we both study pulsars. These are exotic stars that are exceptionally accurate cosmic clocks. And their accuracy gives them a very wide range of fundamental physics applications. The application that we'd like to talk to you about tonight is using a network of pulsars. Whoops, still learning how this thing works. There we go. Using a network of pulsars distributed all over the sky to detect gravitational waves. Gravitational waves are one of the key predictions of Einstein's theory of general relativity, formulated almost 100 years ago. If we can detect these waves using pulsars, this will be the first time they will have been directly observed, and so this would be really transformative science. I'll describe the meaning of these musical notes a little bit later in the lecture. So Dunk and I are going to do this lecture in sort of a tag team style. Here's a brief outline. Dunk will start by telling you what a pulsar is. I'll describe the I'll get it. I'll describe the concept of pulsar timing and why pulsars are so useful. Dunk will then tell you about general relativity. He'll describe what gravitational waves are. And then I'll tell you how we aim to detect these waves using an array of pulsars. Finally, Dunk will make some bold predictions about what we might see using our pulsar telescope. And I'll talk a little bit about our outreach efforts and how you can actually get involved in this research. And Dunk will offer a summary at the end. So now I'll pass the baton over to Dunk.
Thank you very much for the baton, Maura. It's a real pleasure to be here tonight, and thank you again for the invitation to speak. So what is a pulsar? When you think about astronomers and what they do, many people think that they look at stars like the sun, and that's correct, but not all of them look at the sun. Picture behind me is showing the high-resolution image of the sun, taken with a special filter to show it in all its glory. That would be a subject of another lecture tonight. You see the Earth to the scale off to the right there, or the northwest, as astronomers would say, is about 300 times smaller than the sun. The stars that we're going to talk about, pulsars, are several hundred times smaller than that, about 600 times smaller than the Earth. So they're very tiny stars, but very, very important. The sun is in equilibrium. It's supporting its own desire to collapse under gravity by fusing hydrogen to helium in its core. It's stable. It's been stable for many billions of years and will be stable for many more. It rotates on its axis about once a month, and it radiates most of its energy in the optical band. So the stars we're going to talk about, pulsars, are quite different. How are these pulsars formed? It gives you a clue to how different they are. The picture behind me is another optical image. This time it's showing the remnant of an exploding star. This particular explosion, the light from the explosion, reached us in the year 1054 AD. Roughly speaking, once or twice a century in our galaxy, a massive star, several times the mass of the sun, will explode. It will run out of this nuclear fuel that the sun has and collapse under gravity. During the collapse process, the core of the star gets more dense, and the outer layers will rebound off into space, forming this beautiful supernova remnant, as we call them. This is the remnant of a supernova explosion. And this will be lit up in the sky for about 100,000 years. Right at the center here, and we always argue about which star it is, let's say it's this one, is a pulsar. And that is powering the remnant with its magnificent properties. So let's look a little bit more in detail about that pulsar. It's the surviving remnant of this collapsed star. So when we talk about pulsars, we also talk about neutron stars. They're one and the same thing. So what's happened during the collapse is that the protons and electrons have combined together to form neutrons. And these neutrons have eventually become stable enough to support any further gravitational collapse. And the result for certain types of stars is a star about just over the mass of the sun with a size just over the comparable to a large city. So this gives you an idea here, showing a tennis ball scale to Washington, D.C. So the neutron star is supposed to be the tennis ball. You can take this analogy too far. We don't study tennis balls out in space, but what you can think of these neutron stars are really gigantic atoms. That's a very good way to think of them, in fact. So let's look at some of their properties. And these are all come about from this violent birth in a supernova explosion. The first is the density, or the mass per unit volume of the star. It's enormous. There's lots of zeros in that number there. It's basically at or just slightly higher than nuclear density, but it's a macroscopic object. So there's a nice analogy. If you were able to go down to a neutron star and dig up a teaspoonful of material and bring it back home, it would weigh as much on Earth as a supertanker does. It's that dense. So this is very, very exotic material. It's neutrons at very, very high density. What else is unique about them? They spin very rapidly. I told you that the sun rotates about once a month. Well, these pulsars can rotate several hundred times a second. 714 times a second is the record holder currently. To put that into perspective, your kitchen blender is spinning at those types of rates. How does it get those spins? It comes again from the supernova explosion. The skater here is demonstrating the principle of conservation of angular momentum. She is pulling in her arms and legs and doing a pirouette and twirling up to a fast rate. Now we have a little demonstration we'd like to show you here.
I wanted to do an actual pirouette, but Dunk thought it wouldn't be a good idea.
Do you need me to set you in motion?
Yes.
So I'm going to start the chair spinning, and Maura is going to be a large object, and then she's going to make herself smaller and conserve angular momentum in that process, and you will see the spin up. Large and slow,
voila.
Small and fast. Thank you, Maura. So that's an effect that we use in our everyday lives, but the stars use it too, and that's how they get so fast. What else is interesting about them? They're magnetic fields. The sun has a magnetic field, but as it's been collapsed down, it becomes very intense as well. And you end up with a magnet. The star you can think of as a magnet with a north and south magnetic pole, about 1 trillion times the magnetic field of the Earth. That's way in excess of anything we can produce in Hodges Hall, thankfully. But it's actually, the magnetic field is responsible for the radio emission that Maura will talk about in a few moments. Finally, the thing about these stars is they zip through the galaxy very rapidly. They're traveling, we've measured their speeds at up to 1,000 kilometers per second. That's about 0.1% of the speed of light. It's way beyond our everyday experience. There's some numbers listed there for reference of things that we have. The sun the sun and normal stars are moving around at tens of kilometers per second, sort of random velocities. But these stars are shooting up to 1,000 kilometers per second, and that large velocity has again come from this violent birth in a supernova explosion. So hopefully I've convinced you that pulsars are very cool. I'm going to hand back to Maura now, and she's going to tell you what we can do with them.
Thank you, Dunk. So one small correction. Actually, pulsars are not cool at all. The surface temperature of a pulsar is about 1,000,000 degrees Kelvin, which means that it radiates most brightly at X-ray energies. And we actually can't see most of them in optical light. We can't see them with our eyes. This is a little cartoon animation of a pulsar. We actually cannot resolve these stars in space because they're so tiny. This is what one might look like. You can see that this neutron star has a north and south magnetic pole, just like the Earth. Particles are accelerated along these north and south magnetic axes to produce the radio emission that we see. Because these stars are rotating, as Dunk said, sometimes up to hundreds of times a second, they're like little celestial lighthouses, and their beams are rotating in space. If we on Earth are lucky enough that one of these beams crosses our line of sight, every time this beam crosses our line of sight, we're going to see a little blip, or a radio pulse, hence the name pulsars. So this track down here is what we see with our radio telescope as we observe one of these objects. So one fun thing we can do is we can take our observations from a radio telescope, we can digitize it and convert it into an audio file. And I'd like to play some of those sounds for you today just to illustrate how incredibly precise these objects are. I always hesitate to do this because we don't want to give people the impression that we're sitting there at Green Bank with big headphones on, listening for gravitational waves whooshing by. That's not what we do. We don't listen to pulsars to try to discover them or study them. But this is kind of a fun experiment to do, and I'd like to play a few of my favorite pulsars for you. Okay, so this pulsar you're hearing right now is a rather slowly rotating pulsar. It has a period of just under a second. And the thing to really take home from this is the incredible precision of its pulses. So each one of these blips is another rotation of the neutron star. And next I will play a slightly faster one. So this pulsar is rotating about 10 times a second. This is called the Vela pulsar. It's in the Vela supernova remnant. This is my favorite pulsar sound because it sounds like a galloping horse. Okay, the next one is actually the crab pulsar. This is the pulsar that's in the center of the supernova remnant that Dunk just showed you. And this pulsar is rotating about 30 times a second, and you can just make out the individual pulses, barely. Okay, now the next two objects I want to play are a special kind of pulsar called a millisecond pulsar. These are the most rapidly rotating pulsars known. These are actually the types of pulsars that are most useful for the gravitational wave detection experiment that we're going to describe. This first pulsar rotates 173 times a second. Okay, so this is a star that's 20 kilometers across. It weighs more than the sun. It's rotating 173 times a second. This plot down here shows all of these millisecond pulsars converted into musical tones. This pulsar is the F 2 octaves below middle C. It's right here. The next pulsar I'm going to play is one of the very fastest spinning pulsars known. It's rotating 641 times a second. This pulsar is actually this E above middle C here. It's not a very pleasant sound. Okay, so hopefully that gives you an idea of how fast they rotate and how precisely we can measure their spin periods. Now, all of the tests that we can do with pulsars, including this gravitational wave experiment, depend on our ability to be able to measure the arrival times of these pulses precisely on Earth. We want to measure when a particular pulse from a pulsar arrives as accurately as possible. We do this through a technique called pulsar timing. This cartoon illustrates the technique. Here's a little pulsar out in space. Pulsars are actually very weak radio sources, so we need to observe them with very large radio dishes, like the Green Bank telescope in West Virginia. And the name of the game is we observe the pulsars for 10 minutes to an hour or something like that. And each pulse we get, we fold on top of the previous pulse. We add them all together. And we build up a composite profile, like you see here. And then what we want to do is we want to measure the time of arrival of this pulse as accurately as possible. And we do that using an atomic clock at the observatory. Then we want to have a model for this pulsar. What we want to be able to do is we want to predict when's the next pulse going to arrive, when's a pulse next week going to arrive, next month, a year from now, when is a pulse from this pulsar going to arrive. And so we need to model the pulsar to develop this timing model of the expected times of arrival. This has to include the period, of course. Also, pulsars are slowing down as they age, just like people do. They're losing energy. So we need to include this spin down in the model. And there's a couple other complicating factors. So the distance between us and one of these pulsars is changing all the time. The Earth is going around the sun. That's changing the distance. The motions of all the other bodies in the solar system need to be taken into account. The pulsar itself is moving through space. That's changing the distance. The pulsar may have a binary companion, as most of the pulsars that we study for this experiment do. So we need to take into account the pulsar's binary motion around its companion, because all of these things are going to change the light travel time between us and the pulsar and change when the pulses will arrive with time. They're going to mess our model up. So anyway, we spend quite a bit of time taking our times of arrival we measure and fitting this model to them. It's quite fun, actually. It's an art form trying to get the best model you possibly can for a pulsar. Once we've done that, then we can calculate what we call timing residuals. Okay? And the residuals are what we really care about. So it's these things that we're going to search for signatures of gravitational waves in. So these residuals are quite simple, really. They're the difference between the time that we measure a pulse to arrive and the time that we expected that pulse to arrive, given our best timing model. Okay? We can calculate residuals for all sorts of things on Earth. It sounds like a fancy scientific term. For example, our last baby was due to arrive on July 20th. Okay, so that was his expected time of arrival. He actually came on July 1st. That was his measured time of arrival. So he had a negative residual of 19 days. I hope this one has a positive residual at least a week or two, because I have about 3 papers I want to finish before he or she comes. So this is actually a plot of some real data that we used for this gravitational wave detection experiment. These are residuals from a millisecond pulsar. This is, in fact, the one that Dunk discovered that rotates 173 times a second. So these are data over a 10-year time span. This axis here is in microseconds. This is millionths of a second. Okay? And what this shows is that we can predict with very high accuracy when all the pulses from this pulsar will arrive over a span of, say, 10 years. Okay? All these points are nicely scattered around 0. In these data here, there's no obvious unmodeled effect that we are not seeing. Okay? We want to look at plots like this to detect low-lying features due to gravitational waves, and we'll talk more about that in a little bit. So just to illustrate how precisely we can actually measure the arrival times of these pulsars, I've taken this pulsar here and taken its timing model and extrapolated to tell you exactly what the spin period of this pulsar is. I was hoping it'd be exactly 7:45. I think it's a little bit later. But today at 7:45, the spin period of this particular pulsar was 5.757451942123336 plus or minus 0.0000000000001 milliseconds, right? That's 1,000th of a second. So we can predict the spin period of one of these stars with this astonishing accuracy. This is the level that the best atomic clocks on Earth can keep time. Okay. I can tell you that 1 year from today, the spin period will be this number here. A whole year from now, the spin period will only have changed by 1 digit in the 9th place after this decimal. Right? So this pulsar is slowing down, but extremely slowly. I could tell you that on our 50th wedding anniversary in 2053, this spin period will be this. It will only have changed in this 6th digit here. Right? So this is really astonishing that we can time something that's thousands of light years away with this degree of precision. So this is what gives pulsars a good name in the science community and the physics community. Lots of people may not care about pulsars themselves, but we can use them for lots of physics tests because of this remarkable precision. I just have time to talk about one thing before we move on to gravitational waves, but just as an illustration of what we can do with them, I'd like to talk about the detection of the first extrasolar planets. So the first planets outside of our solar system were actually found orbiting one of these exotic stars, orbiting a pulsar. And what the researcher at the time found, he was actually a faculty member at Penn State when I was an undergrad there, and that's what got me interested in pulsars, was that for this particular pulsar he looked at, the period was not steadily increasing with time. It was showing all these funky quasi-periodic modulations up and down and up and down and up and down. And what he realized was that he could explain all of these modulations by fitting 3 Earth mass planets to the pulsar. So he showed that there were 3 planets orbiting this pulsar, exerting little gravitational tugs on the objects and causing the pulsar's apparent spin period to change. This is quite exciting. These planets are actually very similar in mass to the Earth. They're at very similar distances from the neutron star to the Earth. And most of the planets that we've found since that time are not remotely Earth-like, like these planets. Just a caveat, you really wouldn't want to go and live on these. It'd be a very unpleasant place. You'd be bathed in a constant stream of high-energy radiation from the pulsar. This is an artist's impression. Okay, so hopefully I've shown you why pulsars are useful, how we can time them. Dunk is now going to take over and talk about Einstein's theory of general relativity and gravitational waves.
Thanks, Maura. It's actually pronounced Einstein. It's a German name. One of the, everyone has their favorite intellectual thinker. For many people, it's Einstein, but he's definitely up there with the greats in terms of what he's done in terms of just pure human thought. In particular, what I'm talking about here are his special and general theories of relativity from 1905 and 1915. In a nutshell, special relativity deals with the motion of objects as they approach the speed of light. There are many dramatic consequences, which could again be another lecture, but one of the important conclusions from special relativity is that space and time are no longer isolated, distinct objects. It's just part of a 4-dimensional continuum, a space-time continuum that we live in, and you just can't ignore one and just use the other. You have to treat them both on an equal footing. So Einstein then took that theory of kinematics and applied it to revise our notions of what gravity is. Why would he do that, you might think? Well, he did it because Newton's laws, that we all know and love and still learn at school, of course, were being shown. They were so successful at describing the planets initially in the 17th and 18th centuries. But eventually in the 19th century, there were small deviations from Newton's laws which couldn't be explained, that were very significant. So he realized that something was wrong with Newton's theory. It wasn't quite right. So he generalized his special theory to include gravitation. And the way to think about it is that the presence of massive objects, or indeed energy, in space will change the geometry of this 4-dimensional space-time, the three spatial dimensions and one of time, and curve it around the object that is there. And that curvature then is what causes objects in the vicinity to move. So what they do is they just follow the shortest, they just go in a straight line according to them. But what they're doing, they're following the shortest possible path in this curved geometry. It's rather like when you do a transatlantic flight, you wonder why you're going over the Arctic Circle, but that's the shortest possible path. So you perhaps can see down the bottom there of the slide, this is the space-time around the Earth, according to Newton on the left, where the geometry is flat. Bodies would orbit the Earth according to a mysterious force of gravity that acts instantaneously, whereas according to Einstein, the bodies move according to this curvature. They just follow the shortest possible path. And with that theory in place, he was then able to account for these discrepancies, and as you all know, it made him an overnight celebrity. So that wasn't the final word, and we're talking about his unfinished symphony here tonight. There were many, many predictions from the theory that we could talk about, but the one we want to focus on for the rest of the lecture is gravitational waves. So space-time is not a static entity. It's dynamic. It's moving. And it basically, it gets perturbed whenever massive objects start to move around. They produce ripples in space-time that carry energy away from the object, rather like when I drop a stone into a pond, and that carries ripples of energy away from the impact. So as these two stars, shown here at the top of the slide, they can be stars or black holes or people, it doesn't really matter. The gravitational waves get produced as a result of it. As they orbit one another, there are small perturbations in space-time that are greatly over-exaggerated, I should say, in this slide. But these waves of energy, these undulations in the geometry, are propagating out away from the system, carrying energy away from the orbit. So what happens? The bodies move closer to each other and eventually coalesce. They're called inspirals, is the technical term from astronomy. So how do you know that I haven't just told you a load of rubbish, and Einstein as well? Well, we really are very confident about the existence of gravitational waves, otherwise we wouldn't be here tonight. And that's thanks to, in large part, to a pulsar timing experiment, rather like the one Maura was talking about. In this case, a pair of astronomers shown here discovered a pair of neutron stars in 1974 in a 7 3/4 orbit around one another. And basically, it looked like this last slide here. And so Einstein would predict that energy would be carried away from this system, causing the orbit to shrink. Here's a rather technical slide showing their results, but basically down here is an orbital parameter that's mapping out the closest approach of the two stars, shown as a function of time. Now, if Newton's law was golden and was holding for this system, then that parameter wouldn't change with time and the orbit would not shrink. But the data points here are the measurements from pulsar timing of the shrinkage of the orbit, and that line that's passing through them so beautifully is just Einstein's prediction. It's not a fit. It's not one of these model fits like we do with pulsars. It's a prediction from the theory. And every time I look at it, it's enough to bring a tear to a glass eye. But physicists aren't happy enough with that existence of gravitational waves. What they really want to do is detect them directly, not just indirectly, as that experiment showed. I should add that that was a Nobel Prize-winning feat. It was so significant in the physics community. So what are physicists doing right now? They want to detect gravitational waves directly, and the way they do that is they try and monitor the positions of masses on the Earth that are perturbed by a passing gravitational wave. Now, as we're all sitting here in the audience tonight, believe it or not, there are gravitational waves passing through the room in all directions from violent events out in space. And we just aren't sensitive enough to detect them. But let's just do a little demonstration here. So imagine there's a gravitational wave coming through the ceiling. Just humor me for a minute. So this is what would happen. So imagine Maura and I are just two test particles in physicists' parlance. And what we're interested in is the distance between us. So let's let the gravitational wave pop out, coming down from the ceiling down through the floor. And we oscillate back and forth like this. So that's really, it's a little bit more involved than that, but really that's the essence of the problem. The masses themselves aren't moving, it's the space-time geometry is changing. And people are attempting to measure that change in geometry. So in this experiment here, this is in Livingston, Louisiana, there is a test mass, a sapphire sphere at the end of a 4-kilometer long vacuum chamber here, and another one over here. And basically, astronomers are sending physicists are sending laser beams down, back and forth down these arms, and measuring the distance between the center of the station here and the test masses. And if a gravitational wave of significant strength will pass, then those distances will change in a very predictable way. But it's a very challenging experiment. You're trying to measure changes in separations of about a part in 10 to the 19. So a 10 with 19 zeros after it. So it's a very, very challenging experiment. Nevertheless, it is, I believe, going to bear fruit in this decade. The waves that they're looking for have periods of about a millisecond, and they're corresponding to frequencies of binary systems spiraling in our galaxy and beyond. So that's a ground-based experiment. I'm going to hand back to Maura now, and she's going to tell you how we can detect these waves in a complementary way using pulsars.
Thank you. Okay, so Dunk just described an experiment called LIGO, where we have tiny little point masses at the end of vacuum chamber arms, and we're looking for light travel time differences between a laser and a point mass. We can do a very similar experiment with pulsars, except pulsars thousands of light years away are our point masses. Okay, so I'm going to go back to this little drawing that Dunk showed. Here we have some binary system. This might be two massive black holes in orbit around each other. This system is emitting gravitational waves, which means that space-time is fluctuating. Space-time is rippled. Okay, in this same fluctuating space-time sits the Earth and a pulsar. Okay, now go back to what I described about pulsar timing. What we are doing from the Earth is we're measuring the arrival times of the pulses from this pulsar very precisely. If there's any change in the light travel time between the pulsar and the Earth, we have hopes of detecting that through pulsar timing, because a pulse will arrive a little bit early or a little bit late. So if there's a gravitational wave signature, it's going to perturb the space-time, and the pulses from this pulsar will arrive earlier or later than they would otherwise. And so this is the essence of our experiment. We want to look at these timing residuals that I showed you earlier, the difference between the measured and expected arrival times, and we want to detect very tiny perturbations in these residuals that are due to the presence of a gravitational wave source. Okay. One important difference between this experiment and the LIGO experiments that Dunk described are the timescales of the waves that we'll be sensitive to. We're actually sensitive to waves with timescales of years, not milliseconds, as LIGO is. So typically binaries with orbital periods of years are one of our prime sources. You could talk about this in terms of frequency. We're looking at like 10 to the minus 9 hertz or nanohertz frequencies, so very tiny frequencies of gravitational waves. So even though there's a lot of healthy competition, of course, between the pulsar community and the LIGO community as to who's going to get there first, who's going to make this direct detection first, the methods are very complementary to each other. We're looking at completely different frequency ranges. We're going to detect completely different types of sources. So this little diagram just shows what a gravitational wave source would do to the timing residuals of a single pulsar. So a few years ago, some authors published a paper, and they said they discovered a source. It was a black hole binary system with a mass of 50 billion solar masses. This is 10,000 times the mass of the black hole at the center of our own galaxy, at a distance of only 200 million light years. I said only. This is actually a short distance in astronomical terms. Okay, so for such a nearby, massive binary, we would expect to see residuals in our pulsar data that look something like this. We would see this kind of double sinusoid pattern. This is over a period of 7 years, which is very similar to the time spans that we've been observing pulsars. If you look at the vertical axis here, this is tens of microseconds. If you recall back to the timing precisions I talked about earlier, the plot I showed was about a microsecond. Okay? So if something like this actually existed, a black hole binary of this mass and distance, we would see it in our data. So this pulsar timing has already been useful because we can outrule this binary system. We can say these authors were just dead wrong. This thing can't exist, or we would see it in pulsar data. Now this is a nice example of what a single gravitational wave source would do to the timing residuals of a single pulsar. And we can do experiments like this. We can detect gravitational waves with a single pulsar, but we're going to be a lot more sensitive if we use a network of these stars distributed all over the sky. And we look at all of their timing residuals together and try to detect a common gravitational wave signature to all of these pulsars. Okay, and there's two reasons for this. The first reason is that if we have more pulsars, we're simply going to be more sensitive. We can correlate the residuals of all these pulsars. The second reason is that it's just going to be more believable. If we try to claim detection of gravitational wave based on data from one pulsar, you could argue, oh, you know, there's something in the model for that pulsar you're not fitting out properly, blah, blah, blah. If we see a signature from a gravitational wave in the residuals from tens or hundreds of pulsars across the sky, then we're pretty darn sure that we've actually made a detection of a gravitational wave. Okay, this is the concept of a pulsar timing array in the experiment that we're attempting to do. We have pulsars distributed across the sky. We are timing all of these pulsars with radio telescopes. We're calculating these residuals, or the differences between their measured and predicted arrival times, and we're looking for a correlated signature among all of these pulsars. Right? And this correlation analysis might sound a little bit science-y, and maybe you're not quite sure what that means. So let's just do a real-world example. Imagine that instead of sitting in this auditorium, we're all in a big wave pool somewhere. Let's say it's someplace really warm, like the Caribbean. And say a big wave passes through the auditorium. All of our positions are going to move ever so slightly because of this wave. We're all going to be deflected. I could calculate the difference between my position and the position of everyone else in this audience, okay? And then I could plot them on a diagram like this. I'll describe what this is in a minute, but this is expected correlation. Well, I'm describing it right now, aren't I? Yeah. This is expected correlation versus angular separation between pulsars. I could do the same for all the audience members as this wave passed through. For two of you in exactly the same position in the auditorium, I'd expect to see correlated changes in your position. The wave would do the same thing. For someone sitting here and someone sitting over here, I wouldn't see that exact correlation. Because you're in different parts of the auditorium, the wave would act on you differently, and I'd see you move in different directions. Okay, so we do the same thing with pulsars. Okay, this diagram's a little bit technical, but I just really want to show this. And the reason I'm showing it is I want to point out that we have a very specific prediction from general relativity of exactly how this correlation should work versus angular separation between pulsars. If we have two pulsars that are separated by 10 degrees, we can say with very good confidence exactly how their residuals should be correlated. We know exactly what it should look like. We're very certain of this curve. So if we see this type of signature in our data, when we time all our pulsars and do this timing array experiment, we can be certain we have detected gravitational waves. There's nothing else that can produce this signature in our data. Now, currently, our residuals look something like this. Okay, we are not seeing a correlation yet because our timing is just not quite accurate enough. We still have some improvements to make. The hope is that in, say, 2 or 3 years, a signature like this will start coming out of our data. Another few years after that, we may see something like this. Okay? And if we can do this, this will be really robust evidence that we have detected a gravitational wave background, which will be very exciting. Now, there are about a dozen or so researchers in the US and Canada who are doing this kind of research, who are studying pulsars. It's a pretty small community. A few years ago, we realized, hey, this is something pretty big. We should probably organize ourselves and not just have all our own little independent research efforts. And so we formed a consortium. We call ourselves NanoGrav, for the North American Nanohertz Observatory of Gravitational Waves. It'll become a household name soon, I'm sure. Here's a picture of all of us actually outside the mountain lair at WVU last March. What are we doing? So together we're timing 26 pulsars with 2 big telescopes. The Green Bank Telescope in West Virginia that we all know and love, and also the Arecibo Telescope in Puerto Rico. This is a 100-meter dish. This is a 300-meter dish, the largest in the world. Okay? So we're using both of these telescopes to regularly observe a network of pulsars, and we're doing this experiment. We're improving our correlation curve every few months, and we're hoping to start seeing the signatures of this gravitational wave background. This plot shows some of our best residuals thus far. You can see this vertical scale is less than a microsecond now. We're timing this pulsar with precisions of less than 100 nanoseconds. This is 10 to the minus 9 seconds over time spans of 5 years or so. This is about the level we need to detect a gravitational wave background. We're not doing that for all of the sources. Some of the pulsars we still have work to do. There are a lot of complications in this business. The signals from the pulsar have to travel through a whole bunch of interstellar gas to get from the pulsar to us. And some of the perturbations induced by this interstellar gas are many, many times greater than the gravitational wave perturbations that we want to detect. So we need to do a lot of fancy analysis techniques to actually correct for this travel in between the pulsar and us. So the big question, of course, is how close are we? When are we actually going to detect them? That's a really hard question to answer. We don't know exactly how our sensitivity will improve with time. We also don't know exactly what the levels of these gravitational wave sources will be. We don't know how bright they are because we've not seen them yet. This plot gives us an idea, though. This shows our average timing precision on this axis versus time. We've been doing this experiment a little over 4 years now, and here we are. This gray swath here is the expected level due to a supermassive black hole binary background. So due to a background of many supermassive black hole sources in the universe added up together. It's a little bit broad because there's a lot of different theoretical predictions on exactly what the strength of this black hole binary background will be. It depends on the masses of the sources, the distances of the sources, the distribution of galaxies, all this other stuff. But you can see that in a few years, we'll be beginning to hit the regime where we actually have a chance, according to theorists, of detecting something. By 2015, we'll be well in the middle of this swath, which means it'll be quite possible that we will have made a detection of gravitational waves. The pink and the blue curves show what would happen if we could automatically increase our sensitivity by, say, 3 and 10 times. Okay? We could do that by, say, building better instruments on our telescopes. We could also do it, and this is a little bit easier, by just adding more pulsars to the array. The more pulsars we can find, the more we can time, the more sensitive we are. So in that vein, we've realized that, hey, why should we restrict ourselves to collaborating just with people in the US and in Canada? And we formed something called the International Pulsar Timing Array. The idea of this is we want to be observing as many pulsars as possible with all the radio telescopes around the globe. We get more time this way. We get to look at pulsars in the southern hemisphere that we can't even see from the northern hemisphere. This is a little montage of some of these telescopes. There's a few in Europe, the Netherlands, Germany, the UK, and France, one in India, one in Australia. There's a couple new radio telescopes coming online, which will be added to this soon. We, of course, have a bunch of international collaborators. This project is being funded by a $6.5 million National Science Foundation Award to WVU. So this is offering WVU students a really fantastic opportunity to get involved in international research and education. We had our first workshop last summer in Leiden, the Netherlands. Here's a picture of us all. I'm very proud of this picture. I don't know if you can see, but there's a very large number of female students. We have participants from 15 countries. This is a really diverse group. The next workshop will be here in West Virginia from June, actually I think it's 6th through 17th, but the 2nd and 3rd weeks of June. Stay peeled because we'll probably try to arrange a public lecture by one of our international collaborators during this workshop here. Okay, so I'm going to pass it back to Dunk, and Dunk is now going to tell you what kind of sources we might actually detect with this gravitational wave observatory.
Thank you. I was just still in the Caribbean there. So what I would like to say now is make some speculations. We have to, as scientists, stick our neck out from time to time, and this is what I'm going to do next. But again, it's founded on history, and many observations have gone before us. When, not if, we detect gravitational waves, I think it's a matter of when. When we do that, it will be a transformational event. To put it into context, when Galileo first looked at the universe through a telescope, he saw many things that his unaided eyes couldn't, and it's helped cement our place in the solar system. Astronomers have subsequently enhanced those optical telescopes, allowing us to see further and deeper back into the universe's history. With gravitational waves, we're not actually looking at just photons anymore. Optical light is just part of a spectrum of photons going from radio waves all the way to high-energy gamma rays. We've opened that up in the 20th century with telescopes, X-ray telescopes, gamma-ray telescopes, radio telescopes, as you've heard. But those are all photon-based observatories. Here we're looking effectively at gravitons, is the technical term for that. We're looking at the universe in gravity, and it'll be quite a different window that we have on the universe. So we'll be seeing things quite differently, and some sources that are just impossible to see in the optical regime, or electromagnetic regime even. So there are many things that we might detect, and probably many things that we haven't yet thought of. But I just want to give you a glimpse into what the kind of ideas that we're coming up with for sources at the moment. By way of this slide here, which shows a history of the universe. It's approximately 14 billion years old. And as many of you know, we live in a universe that's expanding. And about 13.7 billion years ago, the universe was born in the Big Bang, where all of space-time existed and then expanded initially at a very large rate, known as cosmic inflation, in the early period of the universe, and then settled out into steady expansion to the size that we see today. There are three sources of gravitational waves that are in this low frequency, the nanohertz regime that we're looking at with pulsars. Those three sources are the Big Bang itself, the cosmic inflation era, here at very early epochs, and then at later times, as the universe is settling down, so to speak, the formation of galaxies through successive mergers of smaller galaxies. So let me start with that last one, which I couldn't really say very well. So this is the one that we think we know the most about, and it's that grey swath that Maura was showing you a few slides ago. So the galaxies we see today, indeed the galaxy we live in, every one that we've been able to study in detail has an enormous black hole at the center. It's no cause for alarm. We're not going to get sucked into that. But those black holes we have very compelling evidence based on the motions of stars in the innards of our own galaxy and in many others, that most galaxies harbor a very large, and by very large I'm talking about millions of times the mass of the sun, a black hole with that mass at its center. Those black holes have had to form somehow, and it's believed that they formed through mergers of smaller galaxies, and as the mass built up, then those black holes formed in the earlier universe. So remember, in all of this, when we're looking out into the universe, we're looking back in time. The universe is like a time machine. That's one of the things that makes it so fantastic. The further out you see, you're seeing the universe at its earlier stages. And so when we look out deep into the universe, we can still see the electromagnetic radiation and the gravitational radiation from these events reaching the Earth today. So we're trying to look for the evidence of these galaxy mergers in our data. And we probably won't see a single merger. It'll be an ensemble of galaxies at a certain point in the universe's history, looking back in time. And so that's the basis of this ensemble of black hole, supermassive black hole mergers. A little bit more speculative are the first 2 points in my slide, a couple of slides ago. That is the Big Bang itself and the cosmic inflation epoch. The Big Bang, we know that 300,000 years after the Big Bang occurred, the cosmic microwave background radiation has been detected. We see the evidence for this, for the birth of the universe, but that's an epoch of about 300,000 years after the universe was born. We might be able to see a background of gravitational waves from the Big Bang if we can see far enough, and that should be all over the sky. As the universe expanded, the gravitational waves were formed in this dramatic inflation period when the universe was dramatically changing in its geometry, and we also might expect some gravitational waves from that. I'm starting to wave my hands a bit more at this point, and so you can see that I'm getting out of my area of normal everyday expertise. But these are the type of things that we are looking for. I think the supermassive black holes are really our best bet, but it's the early periods in the universe's history which will be equally dramatic. And there's always the unexpected. You can always try to think about these things, but there are classes of objects out there that we don't know about, and there are indeed things that have been proposed that seem right now completely farcical and fantastical. But there is one particular class of gravitational wave emitters I want to finish with, and those are cosmic strings. The cosmic strings are thought to be large topological defects formed effectively by the cracking in the universe's geometry as it underwent this dramatic expansion in the early epochs. And there's thought, again, to be large amounts of energy stored in these structures here. So these strings here are harboring gravitational energy. And those are thought to be also low-frequency gravitational wave emitters. So that's enough speculation for now. What we really want to get on with for the rest of the talk is how not just we can do this, but we can all do this together and get involved. So I'll hand it back to you, Maura.
Thank you. So yeah, in the next few minutes, I just want to talk a little bit about how we're involving students and how you can even get involved in the search for new pulsars. All of this stuff may sound rather esoteric, cosmic strings and Big Bang, and how could anyone actually understand all these things? But we actually have a lot of high school students in West Virginia and other states that are participating in this research with us through a program called the Pulsar Search Collaboratory. The PSC is supported by an NSF grant to the National Radio Astronomy Observatory in Green Bank and to WVU. The goal of this program is to get high school students actually looking at real data taken with the Green Bank telescope to search for new pulsars. They're not actually doing the gravitational wave detection experiment, but the work they're doing is really fundamental to our efforts. The more pulsars we find, the sooner we will detect gravitational waves, and they know that they're part of this big experiment. We started off on a rather small scale with just high schools in West Virginia. Here are the students from Morgantown High School, and I see Jane sitting out there in the audience. Hi, it's Jane Lark, our Morgantown High School teacher. Now we've expanded. We have 41 high schools involved in 9 different states. These are the schools placed on a map. We have a little group going called the PSC West out in Illinois and Wisconsin and Minnesota. We have over 200 students involved in this effort at the moment. About 60% of them are female. About 50% of them are from rural counties. We're hoping this does a good job of diversifying the physics population at WVU and other universities. The students log on to an online database and they analyze Green Bank telescope data on this online database. It's been a big success as far as getting students interested in science, getting a more diverse population. It's also been a really big scientific success so far. So far, the students have found 3 new pulsars. Our first discoverer, Lucas, was invited to the White House. He got to meet President Obama, and there he is with Obama. Our second discoverer, Shay, will be starting at WVU in the fall as a physics major. She wants to be an astrophysicist, which is great. Here's Shay and Lucas with President Clements. We just had another discovery just 2 weeks ago. 3 students simultaneously found a very fast-spinning new pulsar in our data. This is Alec and Hannah. This is Casey on Skype right here. And these 2 students drove to meet us at Green Bank. They drove 7 hours from Kentucky to meet us at Green Bank 2 weekends ago to follow up this new pulsar that they found. That's how excited they are. So it's been fantastic working with the students. I think it's a really good way to get them into science. And if you are a high school student or an undergrad, you're looking for a research area to get into, gravitational wave astronomy is hot. It's not going anywhere anytime soon. There's going to be a lot of surprises over the next few decades. You might say, but I'm not a high school student and I'd really like to be able to do something with pulsars. Well, you can. You can go to Einstein at Home, this website here, and you can download a screensaver that will actually allow you to download data taken with the Arecibo telescope. Duncan and I are actually involved in this survey. We've been giving these Einstein at Home people pulsar data to process. They're supposed to be processing LIGO data, but they're tired of not seeing anything, so they're processing pulsar data now so they can detect some new pulsars. You can download this screensaver, run it on your home PC, and have the chance of finding a new pulsar like this nice couple in Iowa recently did. So that's the end of our talk. I'd like to thank everyone for coming and giving us the opportunity to talk to you today. Doug's going to close with a few words of summary.
Yeah, so hopefully we've convinced you that pulsars are exciting to study in their own right as neutron stars, but they also have this wonderful clock-like stability that allows us to do explore fundamental physics throughout the universe. And in particular, the experiment that we're trying to get after now is the gravitational waves. It's very tangible that in the year 2015, 100 years after Albert produced his general theory of relativity, that we will make the discovery of gravitational waves around that sort of time scale. So it's really, we believe it's not too far ahead. The challenges, though, are significant. It's not something to take lightly. Maura's described many of the data processing challenges, and I told you also about, we need to understand the source populations more, but there are many people, many talented people working to help realize that. Before we close, I do want to make a special thank you to you all, the taxpayers, because none of this would be possible without your support. I'm really most serious about that. We're very thankful for that. And finally, I would like to thank the college, the university, and the physics department for supporting our research. Thank you very much for listening.
All right, we will open it now to a brief question and answer session. Our ambassadors are in the gray t-shirts. Please wait for them to come up to you. They have a microphone, and so we can hear everyone's questions clearly. So we'll take the first one from Provost Wheatley.
I have a question for Dunk. I'd like you to place the centenary of the theory of relativity with a little bit of context. I mean, here Einstein was, without the internet, without, the kind of telescopes you have. What were his lines of evidence? What did he do?
He really, when I said it was a triumph of pure thought, in a large to a large extent it was. He had an incredible physical intuition, and he actually ignored many of the observations that were known at the time while formulating his theories. He wasn't fully aware of all the data at hand, yet he just had a sense of the way the world works and formulating these theories, and he just saw the beauty in the theory that he eventually came up with. It's, you know, he's really one of a kind. There haven't been too many people like him.
We have one here in the front. In the red.
Hi, I was just wondering, are measurement inaccuracies and uncertainties an obstacle to your work, and have you had false discoveries or any exceptional circumstances where you had to deal with them?
Certainly we make mistakes sometimes. There have been times when we've seen signals in the timing residuals of a single pulsar that look tantalizing, and we may say, oh, we don't understand what that is, and occasionally we will find that there was a clock error at an observatory or something like that, or something in a model for one of the pulsars that we're not incorporating. But that's the reason that we're doing this correlation analysis experiment, right? So if we correlate the signals from a whole bunch of pulsars and look for this correlated signature, those things don't really matter. We can have problems with the model for a particular pulsar. We can have general inaccuracies. We can even have clock errors. We can get our solar system ephemeris wrong. But if we see that correlated signature, it can really only be one thing. So that's basically why we do that, is to try to protect against things like that. Occasionally there'll be a leap second, and we'll forget to account for it, and suddenly everything will go haywire, and we'll see this big, you know, jump in our residuals, things like that.
Our next question's up front.
Thank you very much for this very interesting talk. Really enjoyed it. Duncan, I was interested in your comment about the origin of the universe. Recently, I have seen numerous references to the universe being made up of many universes, polyuniverses, or parallel universes. First, do you subscribe to that idea? What does it do to the Big Bang theory of the origin of the universe?
Well, I'd prefer to stick with one universe, but just to keep things simple. But you certainly can't rule out, you know, when you're getting into some of these advanced theories of, you know, the structure of the large-scale structure of the universe and the origin of the universe, there are many predictions that they make that are currently untestable. Among them, these gravitational waves and cosmic strings, perhaps. So, at the moment, I think the floor is open to many, a large family of theories, particularly in describing the universe at early times. I wouldn't, you know, care to speculate too much about the existence of alternate universes. I think there's probably, if you can have another one, and I don't see why you wouldn't have a Big Bang in that one too, or not, or something, the conditions in that universe could be completely separate. But really I'm getting, or many, the other universes could have quite different properties, depending on the initial conditions.
Other questions? I think we have one in the front.
Could you comment on the speed of propagation of the gravitational waves?
So in general relativity, that is fixed to be at the speed of light. So one of the things that could be tested by some of these upcoming gravitational wave observatories is the measurement of that propagation speed. So Einstein again makes a definitive prediction, which has not been measured yet.
We'll have time for 2 more questions. I see one from a student in the front.
Okay, this is kind of a 2-part question. One, I want to know how hard is it to discover a pulsar? It seems like high school students are doing it, why can't college students? And two, how many have we discovered so far?
So actually, discovering a pulsar, I don't want to say it's easy, but it's definitely within the realm of high school and college students. What we do is we point our radio telescope at a position in the sky, and we analyze the data to look for periodic signals. The actual software that we use to analyze the data is a little bit complicated, but the end result is a diagnostic plot. And this plot has information on it like that pulse profile, like how the signal varies with time and frequency. And it's quite easy to teach our high school students what to look for in these types of plots and how to distinguish a real signal like a pulsar from radio frequency interference from your cell phone or your TV or cattle grid or something like that. Part of the reason that we're doing this program in high school students, part of it is education, part of it is also selfishness, because we have so many plots to look through, and it's very hard to come up with an intelligent algorithm to do as good a job as a high school student can do. I mean, the human eye is very good at pattern recognition, and once you learn what you're looking for in a particular image, the students become really expert at it. Indeed, college students could do it. If people are interested in doing it, they should talk to us. I actually have a grant from this Cottrell Scholar Award to try to get undergraduates in introductory astronomy classes looking at pulsar data in the same way that these high school students are doing, and they're going to look at our SIBO data as opposed to Green Bank data. And that should get started to be kicked off later this semester and certainly next year. I think your second question about how many pulsars there are. So right now we know about 2,000 pulsars. And roughly half of those have been discovered over the past 10 years or so. We expect the number to grow to around 4,000 over the next 5 years, because there's a number of really large major surveys, most of which have the goal of finding pulsars to add to this pulsar timing array. One caveat I just want to point out is that not all of those 2,000 pulsars are good pulsars for our experiment. So for the pulsar timing array experiment, for trying to detect gravitational waves, we really only want the very fastest spinning, most accurate, precise pulsars. So that's why we're only timing 26 of them with Arecibo and Green Bank. Most of the pulsars, we just can't time to this nanosecond level of precision that we need to in order to detect the gravitational waves.
I see. How about one here in the middle for our last question?
How did you find the size and the weight of a pulsar? I mean, how big is it? How small is it? How do you tell that? And how much? What about the weight of a pulsar? How do you find it?
The rate at which they're spinning.
Oh.
So you can take, with the brightest ones, you can take a chart recorder, which is just a pen attached to the telescope effectively, and it moves along with time and records the pulses coming out of the telescope. We can read out the data from the telescope up to tens of microseconds, and so there's plenty enough resolution to see each pulse, and so that the spacing between those pulses as the repetition period, that's the rotation rate of the star. You might be thinking, well, what other things could explain the data? And people indeed thought about that. They thought they might be pulsating stars or binary systems. Really, you can contrive many ideas, but none of them are stable on timescales of billions of years. One thing we didn't point out with these pulsars is, these really fast spinning ones, is that they've been around for several billions of years, since the very early days of our galaxy.
He actually asked how you determine the mass.
Oh, the mass. Okay, sorry, I missed that bit. The mass is deduced when you have a pair of pulsars in orbit around one another. In the simplest case, you can just use Kepler's laws, like we do in the solar system, to weigh each pulsar. But in fact, you have to actually appeal to Einstein's theory to extract the individual masses. There are a number of effects that only that theory predicts that can be measured through this timing technique. And you effectively, if you're familiar with solving algebraic equations, you get 3 equations and 3 unknowns, and 2 of them are the masses.
We can actually measure pulsar masses better than any other stellar masses aside from the sun. We can measure them with extreme precision using these techniques.
Okay, join me again in thanking Drs. McLaughlin and Lorimer.